Thank you for joining. Today we have Stefan Baur from Mercedes-Benz. I hope I'm pronouncing it correctly. And University of Tübingen, Autonomous Vision Group, my previous group. He is working with Andreas there. He started in 2018 as a PhD student. And he apparently first worked on realistic LiDAR simulation for autonomous driving. And later he had quite nice work on motion-based self-supervised learning for LiDAR point clouds. And in 22, he became a full-time machine learning engineer at Mercedes-Benz. At the moment, he is working on online HD map learning. Looking forward to your talk, Stefan. Thank you very much again for coming and giving this talk.
Thank you very much for the very warm welcome, and sorry for the delay. I will just go right ahead and share my screen. Here it says host is disabled, participant screen sharing. Maybe if you can
we
enable
enable
that.
the screen share?
And
Host tools. It's in the host tools.
Make co-host.
Okay.
It will be easier.
Yeah.
Okay. Can share the screen. Okay. Okay, you should now be able to see my screen. Is that correct?
Yes.
Perfect. Yeah, so once again, thank you very much for giving me the opportunity to talk about my work today. So today I would like to give a little talk about how we can leverage motion for LiDAR object detection to do LiDAR object detection completely self-supervised. So we are not using a single human annotation, and in the end we want to have like a LiDAR object detector out of our approach, basically. So yeah, maybe a little bit first about myself. So in 2018, as Fatma already said, I started as a PhD student at Mercedes-Benz and Uni Tübingen. And since now 2 years, I am an ML engineer for driver assistance systems and ADAS. And yeah, I'm mostly interested in learning without human labels. So that involved LiDAR simulation in the past and also this self-supervised learning on LiDAR. So yeah, and in my free time, I really like to go ride my bicycle or my motorcycle. So the question is for me always when it comes to this self-supervised stuff, maybe we can have a look here. Hope you can see this. I'm sharing a video here right now. So the question for me is really, how do we get from this LiDAR scene flow to really good object detector? So we don't want to use human annotations. We only want to use motion, and we want to train a LiDAR object detector that is capable of detecting these moving objects, but also these static ones. And that's what this talk is going to be about today. So skip this one. Okay, and so what's the motivation for this? The motivation is basically that this human labeling is very, very expensive. So, and that is multiple reasons. The first reason is it takes a very long time to do these complex annotations in 3D. So basically, you have to train people what you want exactly, and that takes time, and then you need to hire a lot of labelers, and of course there's services for that available, but still people make errors, you need to correct the errors, you have another feedback loop, and that is very time consuming. And what I think, what we're now coming to as a community is this idea that data and compute is really abundant and cheap, and we should thus use it more to our advantage. And so the idea here is to use motion and the time and consistency over time as a supervision signal without using any human labels. And so that is already concludes the welcome introduction and motivation. And now I would like to talk first about how we get self-supervised LiDAR scene flow out of these point cloud sequences. So this is like a work that we had at ICCV 2021, where we had trained a network that was able to predict pointwise scene flow estimates, and also you can see here highlighted highlight the moving objects basically in the scene. And so first I would like to recap quickly what is actually LiDAR scene flow. So basically scene flow, that means you have somewhere a sensor that can be mounted to a vehicle, And basically you have some objects in a scene, and these objects move, or the sensor itself moves. And what then happens is you record these consecutive point clouds. So you have recorded here some point cloud, and you have recorded here another one, and note how they have like a different amount of points. And now you ask yourself, okay, how did each point in the first point cloud move when we go from the first point cloud to the second point cloud? So it's not about finding absolute correspondences, but it's more like, okay, what's the underlying motion that caused this displacement, basically? And that's what scene flow is trying to answer. And then we also have this motion segmentation aspect. So basically, motion segmentation is segmenting the points in the scene into two classes. So this is one, like the static background classes, and the moving foreground classes. And this is because from the sensor's perspective, there's really two causes of this scene flow. So one is the sensor's ego motion, which causes the apparent flow on the background points, and the moving objects, they cause, they move on their own, basically. And so they have a different motion from the background and kind of stick out there. And existing works, they acknowledge that they have different sources, at like absolutely discretely distinct sources of scene flow, but they, at least back then, they didn't use this information, basically. So that's what we are coming in. So basically, what's just to reiterate, what's the goal here? We have 2 point clouds, PT and PT plus 1. And we want, for each point in the first point cloud, we want to have a displacement vector that tells us, okay, how did this object move? And at the same time, we want to have a network tell us, okay, this is the moving, these are the moving points in the scene, basically. And so the question now is, what makes this challenging? Basically, there's multiple reasons, but the biggest reasons, at least for LiDAR, I think, is that we have like really sparse measurements at the in the distance, basically. But also very closely, like stuff can become occluded and stuff like that. But really, for these faraway regions, we want to have like a high range, very far away from the vehicle. And so we get like very, very noisy predictions here. And you can see, okay, here at this boundary, for example, we're getting very weird artifacts. And so we thought, okay, but this is all just static background. We know that the sensor's ego motion can be condensed into like a single rigid body transform. Why can we not make use of this information? And so the goal of this work was to find a mechanism that can aggregate the flow on these background points and use that to improve the scene flow. And the way this works, basically, is that we, at first, like we have a network. We give the network these 2 point clouds, and the network will give us a very noisy flow estimate. You can see here the vectors are a little bit chaotic, maybe. And so what happens is, excuse me, that we can aggregate all of this scene flow into a rigid body transform, right? Because from if you move the sensor rigidly through the scene, all of the points are, all of the motion of the points can be expressed through this one single rigid body transform. And what ends up happening is, since the background is so dominant, like we have very few foreground points, and we have a very dominant background, like in the percentages, I think on the new scenes data set, over 90% of points belong to the background, basically. I think it's 95 even. And so what happens is you get a very smooth but not entirely accurate background flow, and for the moving objects you get a very bad estimate. And this basically means that you can then leverage this badly fitting scene flow to generate a supervision signal out of it. And what you do is you compute the endpoint error between your warped point cloud and the target point cloud, and then you basically can say, oh, okay, for these points it sort of fits okay, and for these points our aggregated scene flow estimate does not fit well at all, and so we can here use the raw scene flow of the network, and for the background, we use the aggregated scene flow. And what then happens is, what's the idea here is that you use the aggregated flow for the background, and you also only aggregate over the points that your network says are static, and the ones that are dynamic in the foreground, you will basically use the raw network output. So how do
Can I add something?
yeah, sure.
You don't directly predict rotation translation, but you predict it from predicted scene flow. What is the
Exactly.
reason? Why do you not directly predict an RT? What is the benefit of predicting a scene flow first?
That's a good question. I think the challenge with the rotation and the translation is that with the large scene flow field, we can maybe go back a little bit. So if you here predict the scene flow for all the vectors, it's so from our experience, it's a lot more stable than just predicting one translation and one rotation directly, because of the sheer mass of predictions, there is like an inherent regularization if you now squeeze all of this info into a single 4x4 transform, basically. And instead, if you were to predict like these things directly, at least in my experience, it becomes more unstable. But this is something we explored only at the very beginning of the project, and we found this aggregation to work very well, and so we stuck with it. But in the beginning, we tried to predict rotation and translation directly, and we found it to be not so stable. So that's why we
By
went.
aggregation, do you mean something like differentiable fitting,
Yes.
like Ranzak or no Ranzak?
We use this Kapsch algorithm, but I will come into this
Oh,
later. So
okay.
basically,
Sorry.
it's yeah, no, it's fine.
Oh,
So basically, it's a differentiable way to align two point clouds, basically. Yeah,
okay.
and that is a very stable, has been very stable for us. So that's why we used it. Yeah. So, but we will get into this in a minute. You can already see it over here. So basically, now we have like these two point clouds. We have two pillar feature encoders. That's like a bird's eye view encoder. That's like very, let's say, well-established encoder. And then we use this.
So you don't encode the point cloud, but you encode the bird eye view projection of it, or
Yeah, so the pillar feature network that works by so basically you're inserting the points into a bird's eye view grid,
okay.
but you're not inserting like a binary occupancy into it, but like some statistics, like okay, how many points are in the pillar, what's the mean of the points inside of this pillar, what is like the maximum, the minimum extent. So like low-level statistics are inserted into the bird's eye view tensor,
Okay.
basically. And then we use a well-established optical flow backbone. Maybe some of you have already heard of it. And the way this works is you have some initial estimate here, and basically, so we initialize to zero, so like zero flow and zero motion segmentation, and also zero flow confidence weight, and then we iteratively update this for like 6 iterations, and then we have like the final prediction out of it. So it's a little bit complicated what's going on there, but it's not relevant for today's talk, so I would just skip over it. If you're interested in details, I would refer you to the paper. But what we basically did is usually this only outputs a flow, optical flow, but we extended it to also output this classification. So this is basically what's telling us, okay, is this a moving or a static point? And we also uh, edited edited the network that it also outputs a confidence weight. And this basically means, okay, how confident am I in the flow prediction so and so, basically. So there's like a signal for our output decoding, where we have this Kapsch algorithm, which gives us a rigid body transform that we briefly talked about. And basically, we can use the classification to mask the points that we use to obtain this rigid body transform. So yeah, maybe this will bring a bit more clarity. So basically, what is this Kapsch algorithm? So the goal is to find from 2-point clouds the rigid body transform that aligns the first point cloud to the second point cloud. It's like a little bit like a single step ICP because the correspondence here is already known. So like you know which point belongs to the other point basically. And so what you can do is you can solve this differentiably using singular value decomposition, and you can basically weight the influence of individual points in flow vectors by the network confidence, which is what we're doing here. And so what you get out of it is like a translation. And that is, of course, very simple to compute. And you also get this rotation, which is done via this singular value decomposition. And in the end, you have like a full rigid body transform, which you can differentiate, where you can differentiate the flow, the weights, and the points, basically. So you can differentiate the loss with respect to all of these inputs, which is, of course, a very nice property. So that's how we get, yeah.
The question is, you use the confidences as weight then, right?
Yes. Mm-hmm.
Do you
Yeah.
see any benefit to using stuff like more robust Ransack, differentiable Ransack, etc.? I don't know if you are familiar with them, but
Yeah. So I am familiar with them, but I'm not sure if I think it's an interesting idea to try out. Um, so for us, this worked well enough. Maybe if you, so yeah, I think it would be worth to try it. I think, yeah.
another question is, do you see, I always ask the same question, maybe. Do you see any benefit to directly encoding the 3D point cloud, maybe like by voxelizing it? You know, there is this a lot of 3D encoders now, new stuff. Do you think that it would improve performance somehow for SimFlow?
Yeah, that's a good question. I don't think I can answer that to be honest.
Yeah.
So
So I was just curious, but yeah.
yeah, I mean, it's a really good question. What is limiting the current scene flow approaches? And I would say, um, so there's like very promising approaches that do like this. Maybe you've heard of it, neural scene flow prior, which is nowadays more, let's say, performing better. But their biggest issue is always runtime because they do like online optimization, and yeah, maybe that would be the best focus if you want to uh, yeah have some positive impact in this area. Yeah, I'm not so sure if it's actually about the encoded point cloud that's holding the scene flow back at the moment.
Okay. Thank you.
Yeah, so the how did we train this? As I already said, we tried to train this completely self-supervised. So we used a couple of losses here. The first one we used was the cyclic consistency loss. So basically, we insert we run the whole pipeline in forward and in reverse, and then the predictions have to be consistent to each other. We use the nearest neighbor loss, which I will go in detail a little bit later, and the motion segmentation. So basically, okay, how do we get this training signal for the network to tell which point is a static point and which one is a moving point? So first of all, this rigid cyclic consistency loss, that's very simple. Basically, we run the network forward and in reverse, and basically this has to then be close to an identity matrix if we run this forward in reverse, and this is then yeah, used as a rigid cyclic consistency loss. So that is a very, very basic one. And we also have this nearest neighbor loss. And what we do for this one is we have like the first point cloud, we have the second point cloud, and we have our scene flow estimates. And then you can basically warp the point by the scene flow, and then you're here basically, and then you go look for the nearest neighbor in the second point cloud, and you try to minimize this error basically. So for this you can apply over the whole point cloud, and it's really very powerful and also quite robust, we found, despite, you know, there might be some problems with occlusions and stuff like that. So the point here might become occluded in the next point cloud, but we found that to be not so much of an issue. And of course, we can do the same thing for this rigid flow, basically. So as you know, we also have estimated this rigid body transform. So in theory, we can, for each point in the first point cloud, apply this rigid body transform, warp it to the next point cloud, and also compute an error there. And basically, we also minimize this one. And the way we then arrive at these artificial labels, so the supervision signal for the network to say, okay, this is a moving or a static point, is we just let the network predict is this is this error smaller or is this error smaller? So is uh, the raw flow fitting the scene better at this point, or is the rigid bodied flow fitting the scene better? So and to each point where the rigid error is larger, we assign to it this label moving, or if the rigid error is smaller, we assign to it this label static, and then we can basically have like a really simple cross entropy loss where we just use these error measures as artificial labels, basically. Yeah. So really depends on which error is smaller, and so the network ends up predicting which scene flow fits better here. And of course, we did a lot of experiments. So we back then people were really focused on the Kitty stereo flow, which is like recorded by stereo cameras, and we evaluated on that. We used Kitty raw LiDAR data for training. It's really well suited to self-supervised learning, but because it doesn't have any annotations, but we have like a large amount of raw data which we can leverage. We also experimented on new scenes data and also on Carla data, and we mostly looked at this average endpoint error, which is like the L2, yeah, between predicted and.
Were you using a combination of them, or were you training the models separately for each data set?
Separately. So basically, we this is like also an interesting aspect which I've been asked about multiple times now, but yeah, we just trained on one data set and evaluated on the same data set.
And what's the reason? Are the statistics of LiDAR, like sparsity, etc., different across data sets? Is this the reason?
So I think that's one reason that it's really difficult to, or at least if we, like naively, if you just were to throw all of this data in a single pot, you store it and then you train on it, then the performance without taking care or just doing it naively, you will end up with the worst performance on all of the data sets, basically, because the sensors, like for example, Kitty has like the 64 layer sensors, Nucins has like a 32 layer sensor, and it looks very differently, and the mounting position is different and stuff like that. So the point clouds end up looking a lot different in terms of statistics to the network, and so there is not like I mean, you can do some domain adaptation techniques and stuff like that, and I imagine then it becomes better if you actually force the network to become robust with respect to calibration or stuff like that. But if you just naively train on everything, I think the performance is worse. Yeah. So that's that's my experience, but yeah, maybe we just tried this naive setup. We did not try any, let's say, domain adaptation techniques or something like that, where you become robust to the source domain. So the full evaluation is of course in the paper, but at least in 2021 that was kind of nice that we were state of the art on this benchmark, and yeah, also in terms of motion segmentation, that was the first network that was able to do this. So, but for details, I would refer you to the paper. Maybe also one other thing, like a kind of a little sneak peek here in the ablation study. So basically, what was the effect of this motion segmentation? Because we might also just use the raw flow prediction, right? We could just say, okay, all of this cup stuff is too complicated. I just use the simple K and N loss, like the nearest neighbor loss, and predict scene flow directly. And I don't want to use this rigid body transform. And then basically you lose a little bit of performance here. Actually, on the static background, you lose quite a lot of performance, and that's kind of expected. But on the moving objects, you only you lose a little bit of performance. But still, this aggregation and in combination with the motion segmentation, that really gives the benefit here. Yeah. And now a little bit a shift maybe. How can we use this self-supervised LiDAR scene flow that we have now to do like self-supervised 3D object detection? This is a paper that we had in ECCV 2024, so very, very recently. And yeah, the goal here is to, okay, now we have all of this motion signal. How can we leverage it to build a 3D object detector out of it without using any human annotations? So this is what this is now going to be about. So we've seen the scene flow. Maybe I can show it again. Oops, no, that's not the right one. So yeah, we have this scene flow here, and we know for each point in the scene how is it moving, right? So here we have colorized the points according to their motion, and you can see, yeah, it kind of highlights the objects that are moving. Now we are moving ourselves. You can see here should be okay to use this as to bootstrap an object detector. Oops. Okay, and so the first thing we do is we correct basically the whole scene for ego motion. We use this with some off-the-shelf ICP algorithm, so that allows us to track the objects in global coordinates later. And it's a really nice library. I really like it. You can just pip install it and throw in your point clouds, and you get like a rigid body estimate, or like your ego motion you get out of it, and you can do this nice accumulation. It's really simple, works out of the box. I can recommend it. And so once we have that, we have like a scene flow, and we have like corrected it for the ego motion. We can then do this clustering and bounding box fitting around the moving objects. So basically here what we do is, maybe if the video works. Yeah, great. So basically what we can do now is we can just go ahead and use dbScan and fit really primitive bounding boxes around these moving clusters basically. So this kind of means we have like 3D point clouds, we have these 3D points, and now we just used this off-the-shelf clustering algorithm called dbScan, and we use that to fit these boxes around each cluster. So it's not a super strong, how do you say? Not a super strong signal, but it's good enough. Basically, you can see there is also some false positives in the background initially, like because the scene floor has some artifacts in it, maybe. Also here, vegetation is always a bit challenging. But what we can then do is we can track these clusters. And what that means is we can discard any implausible cluster that we have, ideally, right? So we have this ego motion, so we can track in world coordinates, which is kind of neat. We can warp our predictions by the flow, because remember each box has attached to it the scene flow, and we can move the box along with the scene flow, which basically means that we can have a very strict search area, so we don't need to look at a lot of region for a matching future box. So that's kind of nice, and then we can just yeah, track the boxes across the whole snippet of the data set. And this is then the result. If you apply this tracking framework, so now you can see these false positives in the background. They have mostly disappeared. Maybe we have also lost a few good detections, but mostly, yeah, mostly we are left with high quality detections that are actually positives. And we can apply this tracking in forward and in reverse. And yeah, we can just connect the tracklets basically.
Do you adjust the detections based on tracking information?
Yes, yeah, exactly. So this is what this step is about. While we this was now the tracking part, and we can also do like a really simple track optimization. So basically, we know that for passengers of vehicles, like abrupt changes in the acceleration feels really uncomfortable, and so what we minimize here on these track positions is just the jerk, like the third derivative of the observed position. And we also use some regularization term, and this makes the tracks basically be a lot smoother. And we also adapt the rotation of the track, rotation of the box to match the track. So it's like a very simple assumptions there, and we can then improve basically the individual predictions. We also use the median of the observed box size. So that kind of, sometimes this DB scan, it over or under segments the boxes, and by just using the median box dimensions for each track, we can kind of be a little bit robust to that. And also we discard tracks that are shorter than half a second. And you can see the result here. So now we have like this high quality pseudo ground truth. So we have boxes around all of the moving boxes. And now the question is really, can we from these moving boxes, can we generalize to all of the boxes that are relevant to us? So remember, we have like only the moving boxes here now, but actually what we want to discover now in the data set is all of the boxes, like all of the relevant objects for our vehicle. And so basically, this is what we've talked about now, just the pre-processing. How do we arrive at the initial pseudo ground truth? And what we can now do is we can train an object detector on that. And since we use a single shot object detector, so it only consumes like a single point cloud itself, it does not have any concept of motion. And this way it will generalize to all of the relevant objects in the scene, despite only being trained on the moving objects, basically. So what ends up happening is we start. You see here in our initial pseudo ground truth, all of these parked cars were not part of our pseudo ground truth, but since we don't tell the object detector which object is moving and which is not moving, the object detector cannot distinguish between moving and static objects, and so it starts to discover all of these parked cars here as well.
But why doesn't it hurt that you don't have it in the ground truth when you supervise it, right?
Yeah, it does hurt. It does hurt. So of course it would be better to have all of these static objects already in the ground truth. Yeah. So and that's a really a fine balance. If you have yeah. So there's like ways around this, but basically what we're doing here is we're training the object detector with a poisoned data set is what
Yes.
we're doing essentially. So yeah, the object detector during training, it will predict a bounding box here, but it will get a penalty
Yes,
for that.
exactly.
Yeah. And so yeah, I think the important thing is that you at least don't have too many false positives in your
Yeah.
initial pseudo ground truth. If you then also combine this this penalty that the object detector will get here with, let's say, a box here in the vegetation, like give it positive reinforcement to detect some false positives where your tracker messed up or something like that, then the thing can collapse. Yeah, but so the important thing is really to have few false positives in your pseudo ground truth, and then what you also need to do is like what really helps is this self-training mechanism. Basically, what we can do now is we can train on this like inferior pseudo ground truth where we only have like the red curve is like the performance of the pseudo ground truth itself on the static vehicles, right? So at the beginning, there is not a single parked car or a standing pedestrian or parked bicyclist in our pseudo ground truth. And what we then do is we let the network discover these things, and then we feed the network predictions into our tracking mechanism and add the boxes that the network predicts back into our pseudo ground truth. So what ends up happening is we improve the pseudo ground truth itself over the training. So with each here we chose every 30,000 training steps, we rerun the whole pipeline. So the whole pipeline, I mean this one, right? So we have now trained for some time on this inferior pseudo ground truth, and now we just run inference of the object detector over the whole data set. And these detections we insert into our tracking and optimization framework. And what happens then is that the pseudo ground truth will improve over time because this will again discard false positives, unstable stuff, like yeah, and optimize the boxes. And yeah, this way we can over time discover more and more like objects in this data set. But at some point, the performance sort of tapers off. So at some point, we have reached sort of this equilibrium where we have yeah reached the maximum of what we can do here. So it's really self-training. The network is really training itself. It doesn't know that because the tracker is not. We don't optimize through the tracker or something like that. But we, yeah, we really use the predictions itself to discover the static objects and then add that to the pseudo ground truth and train again on this improved data set, basically. Yeah, and we did a bunch of experiments with different networks and different data sets. You can see them here. Like we used center point and transfusion for the networks, and we used Waymo, Argoverse, Nuisance, and Kitty dataset for evaluations. And the nice thing about our pipeline is that it runs with identical hyperparameters for all of these combinations, and it still works well. So that's also something that previous methods were not able to do. They were always had fine-tuned their hyperparameters for individual data sets or networks, basically. Yeah, and this way we were able to beat the state of the art here with our method. And yeah, for details, I think we're maybe a little bit short on time almost.
Stefan, why
Yeah.
did sparsity not affect in that case? Why did you not do dataset specific training for object detection? How is it different from scene flow?
Sorry, can you repeat that?
Like the LiDAR characteristics were not a problem in that case, right? You were able to use the same neural network across datasets. What's the reason in that case?
So here we basically, this is like we did not train on all of these jointly. Basically, we trained center point and we trained it on this data set, and then we did the same experiment with the center point on Argoverse. So we did not mix these data sets here also.
I see. But my question is like, why did it work? Because you still have some parameters, right? Why did it not complain about the differences between datasets?
So with all of our design choices, we optimized for robustness over peak performance, I would say. So if you were now to tune this framework to perform exceptionally well for a way more open data set by maybe improving some threshold or something like that, some strategy, I think there's like still a lot of performance left on the table, but we were really optimizing all of these pipeline steps here. We really optimized to be as robust as possible because, in my opinion, that's what makes it useful. I think the like for example, if you look at this, I have to go a little bit back here, like this KISS ICP thing. I really like this one because you just do a pip install, you run it on your LiDAR data, no matter the source. They've shown it. It works with this. I don't even know what hyperparameters it has because the default is just so robust, right?
Yes.
It works well out of the box, and that's what we try to do with our framework. So don't take any assumptions that would break it on one or the other data set, and really try to build it up of robust components. And this robustness enables it to work out of the box on all of these networks, all of these data sets. Because if you, I think it's like it would be a super large amount of work to optimize it for these data sets. I mean, yeah, we could have done it and just reported on, I don't know, Waymo and Argoverse and optimized for peak performance there. But we said, okay, this is not so useful because people will apply it to their own data set and then they wonder, okay, why is it not working? And then the answer is, yeah, but it was optimized for the Waymo LiDAR or the Argoverse LiDAR, and I don't like that.
Yeah, I mean, it's true,
Yeah.
but sometimes it doesn't work at all, like in the case of Simflow, right? Okay,
True.
thank you.
Yeah.
Is
True.
you said that is all? Do you have more to show or?
Yeah. I mean, I still have some. I think this is like the last slide. So the ablation study. Maybe it's not so super interesting because yeah, we just show here that each component has like brings a little bit of improvement with respect to our super basic implementation.
Yeah.
So maybe if you're interested in that, just check out the paper. Maybe more interesting is some qualitative results here. I don't know
Yeah.
how to. Yeah.
I mean, I asked a lot of questions during the talk, but if there are any questions while we watch the results, unmute yourself and ask or hear as well. I mean, maybe we can stop the recording and move on to more